Okay, so to finalize applications of definite integration, we're going to do a couple examples and then we jump to a new topic. The first one, as you can see, is exercise 5.4.5, finding average monthly salaries, and it goes like this. The statement of the problem indicates you that T months after introducing a new product, sales will be, and then you have a function, S of t, which is in the units of $1,000, and it's given, so the sale as a function of time, which is measured in months, is 750 times t divided by the square root 4t squared plus 25. And the question is, what are the average monthly sales of the company over the first 6 months after the introduction of the new product. So the new product is incidental as far as the math is concerned. So you're going to define a quantity B, which is the average monthly sales over the time period from 0 to 6 months, right? Since the unit of time is months. And by definition of average value, which is the last thing we saw, is the integral, well, you normalize by b minus a, which is 6 minus 0 in this case. And then the integral from 0 to 6 of the function of sales, which is 750 times t divided by the square root of 4t squared plus 25. All this in the square root. And so this would be the average value. The math is the same that we saw last time. It's the value of the integral divided by the length of the interval. The integral represents an area. The denominator has units of length, so it's going to be the average value. Essentially, a constant function which will have the same area as the function that you're going to integrate over that integral. Okay? So this can be, is there a question? This can be performed by substitution, where you define a quantity u equal to 4t squared plus 25. So, well, the first thing you could check, there's a reason for that, because if you compute du, this is 8t dt, so there is, except for a proportionality factor, it's almost what you have in the numerator. Then, given that this could work, you will do the mapping. So 0, x equal to 0 goes to u equal to 25. And u evaluated at x equal to 6 gives you the value 169. So basically plug in. So you have 4 times 36 plus 25, and you would get this. This would also mean that t dt is equal to du over 8. And basically by substitution we can perform the computation above. So this would be 1/6 of the integral. Okay, we can put everything in the fashion to be recognized. This is the integral from 0 to 6. I'm not going to do the transformation yet. 750, the square root of this object, which is going to be the u to the 1/2, and then t dt. So I have isolated this in a factor. So this would be equal to 1/6 of the integral, and then I do the mapping. Be mindful of this definite integration when I use substitution. So u of 0 was 25, u of 6 was 169. Then you have the 750 factor, then you have u to the 1/2, and then you have t dt, which is the u over 8. So at this point I have done all the substitutions necessary for the definite integration. If I stay in the u space, and I could pull out some of the factors which are constant, 750 times 6, well, divided by 6 times 8, then the integral from 25 to 169, then I had u to the minus 1/2 du. So the reason the integration was performed by substitution is because what we get is kind of simple. So you have 750 divided by 6 times 8, then you do the integration, u to the 1/2 divided by 1/2, evaluated in the limits of integration in the u transformation, 25 to 169. So you just evaluate and you can actually multiply by one of these factors. So you would have 750, then times divided by 6 times 4, and then you do the evaluation. So 169 to the 1/2 minus 25 to the 1/2. So I have already multiplied by this factor of 1/2 over here. This has the phase of 13 squared to the 1/2, so actually the computation, the numbers were chosen so that the computation wouldn't be so complicated. So if you perform the division, well, basically what you could have is 125 divided by 4. If you divide by 6, then you have 13 squared to the 1/2, so you have 13. And then you have 5 squared to the 1/2, so minus 5. And so you have 125 divided by 4. And then there's a difference of 8 between these two. Then you do the division, and, well, if you do perform the integration, you have 250. The units of these are on $1,000, though, if you remember. So the average value, which is B, is in the units of $250,000 per month. Okay? I mean, even for the algebra, the function was simple enough, right? I mean, we got like something like perfect squares and then taking the square root. So life was simple in this case. It's because of the choice of the function. But the idea, again, the average value is basically a constant such that the area under the curve over the interval of interest will be the same. That is the whole idea of this average value. And we will do a final remark about that. Before that, though, we will do another example, which is 5.4.6, which is the temperature in Celsius. Well, we're going to call it T. The units are Celsius. Celsius with S. So measured from basically from an initial time, which is 6 a.m., so 6 in the morning, to 6 p.m. And the function is given to us is of the form, well, the temperature as a function of time is 3 minus T minus 4 squared divided by 3, where the time goes from 0 to 12 if we measure in hours, right? I mean, so you have gone from 6 a.m. to 6 p.m. There are 12 hours. That's why you have the time interval from 0 to 12. There are two indications. The first one, which is A, is to find the average temperature in the city during the workday, which is basically by definition from 8 a.m. till 5 p.m. And, well, the problem is, again, in this in terms of this average value way of thinking. So 8 a.m., if you think that the 6 a.m. was the reference, which was the 0, it's basically T equal to 2. 5 p.m. is T equal to 11. So you have transformed from the clock time to the units that you have chosen with the reference of 6 a.m. as a 0, and you only have to compute. So the average temperature over this time interval is, well, first you divide by b minus a, right? 11 minus 2 in this case, and then you perform the integral from 2 to 11 of the function that you were given, which is 3 minus, and then a quotient, t minus 4 squared divided by 3 dt. So you have 1 over 9, and then the integral, so you have basically 3t, by the first integration, you will put some limits, then you have t minus 4 cubed over 3 times 3, just think about it. So one of the 3 goes out, and then you have squared. This has to be evaluated between 11 and 2, though. So far so good in terms of the integration. You just have to finish the computation. And, well, This one is basically easy to perform because we have a linear function, so it will be the difference. In fact, it will balance. So you have, okay, 1 over 9, then 3 as a factor, and then the difference, which is 11 minus 2, but this is going to be equal to 9, so it's going to vanish. And then you have the two limits of integration for the second function. So this is minus 11 minus 4, so you can plug in the first or the upper limit of integration, 11 minus 4 cubed. And then you have the factor of y9, don't forget, and then you have the 9 from here. And then you have the plus because of the sign, so then you have here 2 minus 4 cubed, and then divided by 9 times 9 because of the sign. So this gives you a 3. As I was mentioning, this is just a linear function, so this is easy. Then if you do the computation, so this is minus 7 cubed divided by 9 times 9. Then you have, well, minus 2, but this is cubed, so you have the minus. So 2 cubed, it is 8, and then 9 times 9. And if you do the computation, basically what you get is 3 minus 343 plus 8 divided by 81, which if you do the computation is minus 4/3. So I think the virtue of this example is basically to interpret from the information of the problem what is the interval of integration, which are the units. The function is here. Again, most of the problems in the textbook, not precisely in the exercises, but in the lecture material, are chosen easily enough that the simplest concepts can be understood in the first time review. So, well, the function is a piece of info that you're given. It's basically how to learn to solve the problem, which is not precisely just, just the pure math, but as an applied person, if you're a business person, you have to interpret from your physical world what is the math behind it. So that is the first part of the problem. The second part is, I will keep this name, it will be useful. At what times, well, we put times because we will see that we will have a quadratic equation, so you have to decide if the two solutions to the quadratic equation are meaningful or not. So at what time or times during the workday should we expect the temperature to be the same as the temperature in A? So before we proceed, look, what we found in A was the average value. Essentially, a constant temperature such that the area over that interval is the same. Now, what we're going to do here is different. Here, we have a function for the temperature as a function of time, and we want to find which is the exact time in which we obtain that temperature. So it amounts to solve an equation. So in terms of B, you have to find a time which we're going to denote TA in the interval from 2 to 11, such that the temperature evaluated at that time is precisely the average value, which was minus 4/3. Okay? So this is just solving an equation. So in this case, what you have is minus 4/3 equal to the temperature as a function of the time, and I plug in the value of TA in the function, which I want to discover. Then 3 minus TA minus 4 squared divided by 3, so you will solve the quadratic equation. TA minus 4 squared divided by 3 equal to 3 plus 4/3. You pass to the other side, and then you also do that. So, well, you can actually multiply by 3 too. So you have 9 plus 4. If you multiply by 3, everything. So this is 13. And then you take the square root. So TA minus 4 is equal to plus minus the square root of 13. So, well, remember the time or times, it's precisely because of that. But one of the solutions is actually not going to be meaningful, because if you consider the minus sign, so, well, what you have is basically TA equal to 4 plus minus square root of 13, and you have to figure out if both are meaningful. So if you compute 4 minus the square root of 13, that is 0.39, and that is not in the interval from 2 to 11. So you discard that solution because that is the space of times that are possible. So the other possible answer is 4 plus the square root of 13, which is 7.61, and that is actually in the interval from 2 to 11. So from the two solutions, the one that you will choose is actually this one. So TA is approximately 7.61, which is the positive one, okay? Then, in terms of the time, it's 6 a.m., which is the starting time, plus this time difference, 7.61 hours. If you do the conversion, it's 1:37 p.m., okay? So, look again, just to stress the concept. The average value obtained by the integral is basically a constant such that the area over the interval of interest is the same for that constant function. We just happen to find a time where that value is attained. That is the interest of this second problem. To finalize this, we will indicate two possible interpretations of this average value, and it's not gratuitous. There is a reason of interest to make this interpretation. So, two interpretations of the average value. So the first one is the following. Let's say that you have a continuous function on an interval AB, and big F of x is any antiderivative of little f of x over the interval. Okay, so in this case, the average value, b, satisfies by definition b equal to the integral from a to b of f of x dx divided by b minus a. This is the way we define the b. And, well, this is f of b minus f of a, knowing that big F is the antiderivative, divided by b minus a. Now, if you see this form, now you see what this represents. This represents an average rate of change for the big F over the interval AB. Okay? In a way, if you think about it, it's like an average slope for the big F, knowing that big F is an antiderivative of little f. Okay? So there is one interpretation, especially for the business students, which makes more sense because you are more, in terms of the derivatives, the concept of the marginal pops up frequently on the discipline. So one example in terms of this possible interpretation is that the cost, C of x, of producing x units of commodity, and, well, just by definition, trivially, the function c, it is an antiderivative of the marginal cost, which is the derivative. So, I mean, it's a tautology. So c prime of x is the derivative of c. That's all what you need to know. So in that case, the average rate of change of the cost over a range of production, let's say that the range goes from A to B, equals the average value of the marginal cost over the same range. So, I mean, basically think that big F is the cost, little f is the marginal, which is C prime, so it is just plugging in that. Again, what you obtain with B is an average derivative. Okay, that has the shape of a derivative for the cost. So in terms of the marginal, it's basically an average marginal for which the result, if you interpret the result as the integral over the interval, is exactly the same. So that is basically applying the average value to the marginal. The second is more geometrical, and I think, quite frankly, that that is more useful. So the second interpretation is to think of the average value of f of x on the interval ab, let's say for a function f of x which is greater or equal to 0, and that can be interpreted geometrically. And this is something that I have said before, so perhaps I have not written it, but I have stressed the concept in the previous examples. And so if you rewrite the integral formula for an average value, what you have is b, by definition, is 1 over b minus a, integral from a to b of f of x dx. So what does that mean? That b minus a times b is equal to the integral from a to b of f of x dx. Now, what we know, especially for these kind of functions which are non-negative, is that the integral is the area under the curve y equal to f of x over ab. And, well, this is basically the area of a rectangle, where the height is b and the width is b minus a. So, to finalize this topic, it is what I have been saying in the last two examples. Let's say that you have a function, okay, and this is the interval ab, and let's say that b is basically this value. So this is the x-axis, this is the y-axis, this is the curve y equal to f of x, and this is b. What is the whole idea? That you have a constant function such that the area of that constant function over the interval is the same as the area under the curve. Okay? I mean, here you have an excess, like this is above b, this is below b, but hopefully the area will be the same, right? So the effect will be the same. If I choose a constant function such that it has this average value, the area under the curve for that constant function will be the same. So you have chosen a constant with the same effect, defining the effect as the integral over the curve. That is pretty useful in applications where the area has an interpretation related to your program. One example is stuff or relation between the cost and the marginal. The other in cases of physics when you think about work or about power. So that pops up pretty frequently. So geometrically, I think it's, I mean, the effect is pretty much the same if you choose a constant function where the effect is the area. So this would be the end of the topic. Now we start the new section on integration by parts. So we are back to schedule. And so it's possible that you have seen this technique before. If not, I will just briefly explain the technique and do some examples in order for you to understand it. So integration by parts is an integration technique based on the product rule for derivatives. Okay, who has seen integration by parts before? I'm almost sure that 1/3 of the people might have seen it. But, well, in any case, if you haven't, let's say that you have two functions, u of x, v of x, which are differentiable. And then you know the formula for the derivative of a product. Let's say that you have the product u of x times b of x, and then you have the derivative. So you have the rule, right? First, okay, and then u times the derivative of b with respect to x plus du dx times b of x. Okay? So that we know. Now, if you think in the mentality of how we obtain some integration rules, basically, from all the rules of derivatives that we knew, we inferred the integration rules just by going back, knowing that the integral is basically the antiderivative operator. So the technique will be the same. Knowing that we know a formula for the derivative of a product, we will obtain an integration rule based on this formula that will help us to integrate more complicated functions. So what we will focus is actually something of this kind. If you pass this to the other side, and then you focus on this term, what you will have is that u of x times db dx is equal to the derivative of the product, u of x times b of x, minus this term, b of x du dx. At this point, I have only passed one term to the other side. Now what I will do is to perform an integral, and I will obtain a useful formula based on the derivative for the product. So let me perform an integration where I will have an integral of this stuff. This is the integral of u of x db dx. I integrate this dx, and then this is equal to the integral of the derivative using linearity, and also the fact that the integral of the difference is the difference of the integrals. Dx, so performing this one, and then the second integral of b of x du dx dx. Okay? So far, I have just played with equations, perform an integral, and it is what it is. I cannot go wrong. The first one is easy because, okay, the integral and the derivative, and I'm performing indefinite integrals at this point, they're inverse operators. Perhaps I'm omitting the constant of integration, but for the moment it doesn't matter. So here you have integral of derivative of this stuff is precisely the stuff, u of x times b of x. Then I have minus the integral of this, b of x du dx, okay? So all the equations that I have used at this point have led me to this equality, and this has a more compact form. So you probably have heard of this in another fashion. If you recognize each of these terms, what you have is integral of u db equal to u times b minus integral of b du. Who has seen the formula in this fashion before? Okay, more people, right? So this has a name. This is the integration by parts formula, which we just derived from the formula for the derivative of a product. And, well, I mean, this is just a simplifying notation where we have recognized that db is db dx times dx, and du is equal to du dx times dx, okay? So we have just used that notation. So, I mean, if you think about it, okay, I use the formula for the derivative of a product, and I have changed my problem. Instead of computing these, okay, these ones are easy, assuming that I know them. Excuse me. And then I have to compute this integral. So hopefully, I have reduced my workload in the sense that this integral should be easier than this one, because if not, there is no point in the transformation. Okay? I want to simplify my life, not make it more complicated. And so whenever you make a choice of the u and b, you have to realize that you make your life easier and not worse. That is the general advice. So the advice written is that if we find u and b such that the integral that I'm looking for, which is of the form u db, can be expressed in the form u db equal to ub minus integral of b du, and hopefully this is the term that we intend integral of b du to be simpler to compute. okay? So keep that in mind. For polynomials, it's kind of easy to see where it goes. I mean, if you think about it, when you have a polynomial and you take the derivative, you reduce the degree by 1. If you integrate, you increase the degree by 1, so you know which way to go. It will be in the combination of not precisely such easy functions where you will see how to be mindful of the choice. And because the nature of the course is learning by example, regardless of the fact that you might be new to the topic or more experienced in the topic, we have to do some exercises for you to learn. So the first exercise is, okay, using integration by parts, which is to find the integral, it's indefinite, of x squared times natural log of x dx, okay? I know, well, the nature of the course or of this exercise is to put this in the form u db. So to make the statement clearer, you have to choose u and b such that the integral of b du is easier to evaluate. So, and if you think about it, okay, you have two options in a way, right? Starting from that. Which one to take as u or as dv. What you can think is that, well, the derivative of natural log of x is 1 over x. So even if you obtain a polynomial on the other side, the factor related to the natural log of x in the other side will be 1 over x, and you will obtain some simplification. So what you can propose is to use u as natural log of x, which would have a du equal to 1 over x dx. And then what if you have, if you remember, is of the form u db, so you have to identify what is the db. In this case, the remaining terms would give you a db of x squared dx, right? So b would be the integral of x squared dx, and then you do x cubed over 3. For the moment, you can omit the constants. And this simplifies a little bit the life because let's say that you have x squared natural log of x dx. Identify this as the u, this stuff as the db. So what you would have is ub minus integral of b du. Since this is of the form integral of u db, I have already put it in that fashion with the choice of u and b's. So you plug in first what you have obtained in terms of u and b. So you have x cubed over 3 as the b, and then natural log of x, and then the integral of b du. So b is x cubed over 3, du is the x over x if you want. So you will have a cancellation, which is what I was mentioning before, right? So you have x cubed over 3 natural log of x, which is standing for this term, minus x squared divided by 3 dx. So this one is easy to perform, and that's why we didn't lose too much if we chose u as natural log of x, because we would have the factor 1 over x, and then we could perform the integral easy just by polynomial rules. So here what you would have is x cubed over 3 natural log of x. Then you have performing the integration minus, well, you have the 1/3 factor, x cubed over 3 again to account for the x squared, and then plus a constant of integration. This multiplies. So then you have x cubed over 3 natural log of x minus x cubed over 9 plus a constant of integration, okay? But if it's the first time that you learn this topic, part of the learning process is to precisely find which are the u's and the b's. That is where you start, and once you learn how this technique works in terms of the kind of functions that you get as example, you have the technique. Then you're able to perform it, assuming that the integral is easy to be performed by means of this integration by parts. That might not be always the case. But to outline the procedure, if you see we have learned by example in the sense that first we present the idea, then we do an exercise, then we land the concepts to generalize. The procedure would go like this. So the first step would be to choose functions u and b such that f of x dx equal to u db. That's basically, this is what you want to integrate. We could have done different splittings if you think about it. Okay, choose the other one as the u, then, or choose a combination x natural log of x. You can do many stuff, but the problem is that you have to choose something that is appropriate. If not, you might complicate your life and make a bad choice and end up with a worse integral. So you need to have an eye on when this integration can be helpful, or this integration technique. That would let you recognize that this integral of f of x dx will be of the form u db to be done by integration by parts. So you pick a function u such that the u is simpler than u, and the db that is easy to integrate. So this is kind of anticipating when we will do the computation later. So the second is, or the second step is to organize the computation of the u and b, in the sense that you keep track of what is u, what is the u, what is db, and therefore what would be b, which is the integral of db. Okay? The last step is to complete the integration. Actually, I'm curious. For the people who have done this before, did you always do this intermediate step? Yeah? Have you done it? So, look, this is for the first time that you do it. You have to keep track of what is your u and what is your b. Because if you don't do it, again, you can get lost in the computation. So, if it's the first time, keep track of what is u, what is db, then take the derivative and find du, integrate and find b. That is essentially the step. So, you complete the integration by finding the integral of b du. In that case, the technique again tells you that the integral of f of x dx is equal, okay, you have chosen this u and b such that this is in this form. By the formula for the product, this is ub minus integral of b du. And then, of course, you have to add a constant of integration at the end. Now, basically like a final suggestion, how to choose u and db. Again, you have many choices, but probably only one is the optimal. You have to get some insight and experience, which means that you have to practice. So actually, if it's really the first time that you see integration by parts, I would really recommend to go over the textbook problems, the suggested problems, because if you're not familiar with the technique, the only way you learn it is by doing many exercises. That's my advice. Regardless of when you learn integration by parts, either in high school or in university, the only way you will kind of like develop an eye on how to do this one is by doing several exercises. So that's my 2 cents. And after this, we will perform an exercise. So, we will choose exercise 6.1.2, which is the integral from, well, it's indefinite of x e to x dx. Now, perhaps I will motivate a little bit. What would you choose as u and db in this case? What happens if you take the derivative of the exponential? What do you get? The same thing times a factor of 2, right? Okay. What happens if you take the derivative of x? You get 1, right? You get a simplification. So there is a loose idea that perhaps the choice so that if I have the derivative of the x on the other side might simplify my life later. That will be the inspiration in order to perform this exercise, because if I choose u equal to x, then I would have the u equal to dx. Remember that the integral is of the form u db, so that would mean that db is equal to e to the 2x dx. Now, how can I obtain b? By integration, but in the case of the exponential, it's pretty easy. This is equal to e to the 2x divided by 2. So if I were to recognize perhaps this as my u, and then this as my db, this would be equal to ub minus integral of b du, and then I plug in, right? So I would have x times e to the 2x divided by 2 minus integral of b du, e to x divided by 2, and then du, which is dx. So now you see why we had the simplification, because essentially the derivative became 1. And then you have an exponential times a constant factor, which you can integrate easily. That's why we made this choice. Again, we're making our life easier and not more complicated. Okay? So, well, essentially, we have to perform the end of this computation. So this would be equal to x e to the 2x divided by 2 minus 1/2, and then you have, again, the integration e to the 2x divided by 2, so that you recover this. So this is from this term, then this is the, when you take the derivative, you have e to the 2x with the canceling, and then you have a constant of integration. So you can factorize here, basically by a factor of 1/2, x e to the 2x minus e to the 2x divided by 2, and then plus a constant of integration. It doesn't matter for the constant, I mean. Even if you multiply or divide, you're done. So, I mean, if you got lost in the computation, this term is coming from here. This factor is coming because you have the antiderivative. Okay? And then you can factorize, and then you have the same thing. If you didn't follow, please check the computation at home. We will finalize, well, with a couple of examples. 6.1.3, where we would have the integral of x times x plus 5 dx. Now, part of the problem that we faced before is obtained here. Because look, I have a function which is the square root of x plus 5. So I know that the derivative will be cumbersome. If I choose the u as x, again, I will get a simplification. That would help. So in this rationale of making my life easier, if I choose u as x, then I have the u equal to the x. And then if I choose the db as the square root of x plus 5 dx, which means that the derivative of b with respect to x is the square root of x plus 5, which is equal to x plus 5 to the 1/2 dx, I can just integrate. And then b would be equal to 2/3 x plus 5 to the 3/2. And think about it, you take the derivative, you have a cancellation of the factors, and then you have the factor of 1/2. So I have made this choice in order to make my life easier in the last terms. Again, recognizing that you have integral of x times square root of x plus 5 dx, where this is the db and this is the u. Then you would have, okay, integral of u db equal to ub minus integral of b du. Then you plug in all what you have obtained, okay? So the u is x, b is this. So you have x times 2/3 x plus 5 to the 3/2 minus the integral of b du. So you have integral 2/3 x plus 5 to the 3/2, and then the u is equal to dx. So if you want to recognize, this is u times b minus integral of b du. Okay? So this is actually easy to perform because we just have a polynomial, and actually the argument has a dx. Well, if you were to define another variable x plus 5, the dx is the d of the argument inside. So you simply have to evaluate. So you have 2 times x plus 5 to the 3/2 divided by 3 minus 2/3, and then you do the, well, keeping track of the terms, right? So you have x plus 5 to the 5/2 divided by 5/2, which will flip at the end, plus a constant of integration. So you have 2x times x plus 5 to the 3/2 divided by 3 minus 2 times 2 divided by 3 times 5, x plus 5 to the 5/2 plus a constant of integration. So you can simplify, and that would be the end of the result. In fact, if you put it in a nice fashion, well, just finalizing these computations, you have 2x times x plus 5 to the 3 halves divided by 3 minus 4 times divided by 15 of x plus 5 to the 5 halves plus a constant of integration. And this is the end result. The last comment in this exercise is that integration by parts is not the only way to perform this one. Because if you go back to the original shape of the integral, well, you have something difficult, which is the square root of x plus 5, and then something nice, okay? So what you could have done is also perform a substitution method where you define the u as this variable. And the point is that the difference between the simple thing and the u is basically a constant. So you could then manipulate by using substitution to perform the same integral. So actually that's a good advice in terms of integrals. There's not always a single way to do it, but of course, if the computations are correct, you will end up getting the same. If perhaps in a different shape, but still the same mathematically. So as a note, we just have to indicate that this integral could have been solved by substitution. And we will do it. So you have the integral of x times the square root of x plus 5, the x, where you define a u variable, which is equal to x plus 5. So x is equal to u minus 5, but still the u is equal to dx. So there's a linear relation, then this is easy. So if you were to substitute the x is equal to u minus 5, then you have u, which is x plus 5 to the 1 half. And I think now you see why we could have done this also by substitution. Because look, you can split this in the difference of two integrals, right? The first one will just be a polynomial that you can integrate easily. The second is still 5 times u to the 1 half. So you can perform it anyways. If you do the splitting, actually you have u to the 3 halves du minus 5, the integral of u to the 1 half du. So here you can perform it, and then, well, if you do basically the balancing of the terms, you have 2/5 of u to the 5 halves. Think about it, you perform the derivation, so 5 halves vanishes, then you have 3 halves, so you have the first one. And then you have minus 5 times, well, what you would have is 2/3, then times u to the 3 halves, plus a constant of integration. And if you put everything in a nice fashion, then what you will have is 2 times x plus 5, going back to the relation between u and x, which is to the 5 halves, divided by 5. Then you do the multiplication, 5 times 2 equals to 10, divided by 3, u to the 3 halves, so x plus 5 to the 3 halves, and then plus a constant of integration. The last thing to observe is that it might seem that it's not the same, but actually the terms are equal. Look at the way of the final answer over here, where is the term of the final answer here. So they might look slightly different, but they're actually the same answer. If you do the computation, basically, let's say that you start from 2x divided by 3 of times x plus 5 to the 3 halves minus 4 over 15 of x plus 5 to the 5 halves. So first of all, you could factorize x plus 5 to the 3 halves, then you have factorization to x over 3 minus 4 over 15 times x plus 5. So that would be equal to x plus 5 to the 3 halves. If you do some computations, you have 2x over 3 minus 4x divided by 15. Then you have the other term, minus 4/3. So you have the division. Then you have x plus 5 to the 3 halves. And then if you do the computations, you have 6x over 15 minus 4/3, which would be equal to x plus 5 to the 3 halves of 2x over 5 minus 4 over 3, which would be equal to x plus 5 to the 3 halves of 2/5 of x plus 5. So you're going to add and subtract the same fact, well, the same number, which is a 2. So this is plus minus 2, so it doesn't matter. Minus 4/3. And then what you would have is x plus 5 to the 3 halves multiplying 2/5 of x plus 5 minus 10 over 3. And that is the final solution. So if you compare basically these two forms, we go back to this answer. Okay? So This is as in the substitution method, so this gives the quality. If you have not done the computation, I would encourage you to check the answer. We will see it next time, and we will start the topic in the next class.
With one of the computations,
Right.
you had with integration by parts.